Now that we have the method, the query string, and the path, we can actually create a new request. To do that, we can come to the bottom of our function and replace the unimplemented macro with an actual return value. So our function returns a result, so we have to wrap the request in an OK. And now we just create a new self. We have to pass the path, the query string, and the method. This, of course, will not compile because the request expects strings that it can own, and here the path is actually a string slice. If we can find the path, we see that it is a string slice. Same for the query string. The request expects an option wrapping a string, but we are actually passing an option wrapping a string slice. The easiest thing that we can do is to convert these string slices to actual strings. So we can call to string on the path, and we have to actually say that this is the path key. And we can do the same for our string slice inside of the option. So if we call to string on that, and we also remove the reference here because we don't need it anymore, we see that now we can successfully create a request. And our code will compile successfully. But is this the best thing that we can do? Let's think about the drawbacks of storing owned strings inside of the request instead of actually storing the string slices. And here is an example of how our request would look like in the case of this request here. So we have our buffer that lives somewhere on the stack for the server run function. And we see that in the buffer, we have the method, we have the path, we do have some query parameters, and we have the protocol. When we create a request struct from this buffer, we generate a method enum from the method here. This is fine. And then for the path and the query string, we actually have to copy all of the contents of the path and then make a new heap allocation to create a new string and copy that on the heap. Same for the query string. The benefit of copying from the buffer into new strings on the heap is that now the request owns these two strings, and this means that the request can mutate them if it wants. But in this case, we would never change the contents of these strings. For our purpose, whatever we receive over the network and we store in this buffer is immutable. We would only want to read it. So it doesn't really make sense to copy the strings and do unnecessary heap allocations when instead we can just store string slices directly in the request struct and they will point back into the buffer. This is how that would look like. Doing this, we ensure that there is no unnecessary heap allocation and no copying of bytes. Let's go back to the code and implement it like that. So we have to change the string here to a string slice, and we have to do the same for our string down there. And also now we can get rid of the toString. We'll have to return the reference here, and all right, now we can create the request using string slices, but we see that the compiler complains. Let's actually compile that in the console so we get a better look. If we run cargo build, we see that the compiler complains that it's missing a lifetime specifier. This is for the string slice in the query string, and if we scroll up, it has the same error for the path, which is also a string slice. Before we actually explain what lifetimes are, let's start talking about the problem that they solve. If we come back to our memory representation here, we know that we have some buffer that lives in memory somewhere, and then we have a struct request which has two references into this buffer. This is fine, but what would happen if we deallocate this buffer while the request still exists? And after we deallocate the buffer, we try to use the path variable, for example. This would lead to undefined behavior because this pointer now points to dead memory. This is known as dangling references or use after free, because we're trying to use memory after we have freed it. Another way to rephrase this situation would be to say that the request has a longer lifetime than the buffer, right? Because the request outlives the buffer and then its references are dangling and they're pointing to nothing. The question is, what can we do to prevent this? So for example, when we are writing C or C++, we always have to think about the lifetime of our variables, because in those languages, there is nothing stopping us from deallocating the buffer while we are still using the request. The worst part about this is that the code will compile successfully and will find it at some point at runtime. And this is really not a problem that we want to catch after our code is in production. On the other hand, we have all the higher level languages that have garbage collectors. And in garbage collected languages, it's impossible to have dangling references because the garbage collector will never deallocate the buffer while there are valid references to it. So this problem does not exist in those languages. What is great about Rust is that it gives the same guarantees that the garbage collector gives, namely that there can be no dangling references in our code, and Rust does that without using a garbage collector. The Rust compiler can statically check all the references in our code and ensure us that there are no use after free cases. This means that there are no performance penalties, unlike languages that use garbage collection. So to recap that, in Rust, if our code compiles successfully, this means that there are no dangling references in it. To be able to statically check all of the references in our code, the Rust compiler needs some help from us. This is where these lifetime specifiers come in, because we have to explicitly annotate some of our references with lifetimes so that the compiler can figure out what they are pointing into.